Hello guys. Good morning. Good morning to all of you. Today in this session, we are starting on base nuclear physics. This is the first part of nuclear physics, and I think it will take approximately 15 to 20 lectures to cover our whole nuclear physics part. Okay. So we'll be covering the nuclear physics in such a way that it covers both the syllabus of CSIR-NET and GATE. So in GATE, little bit of extra thing is given like accelerator and detectors. Although those things also come in your CSIR-NET exams, so it is basically the same. So now, without any further ado, let's start. Is everything is all right? Is everything is all right? Okay. Okay. Can you start? So we are starting basic nuclear properties. Okay, so before we move forward, let us go through the syllabus. So this particle physics portion we have already covered. Everything has been covered. Yes. Now, in the nuclear physics part, what we have basic nuclear properties. So this is the first thing we need to cover, basic nuclear properties, and we will cover the first part of it. It includes size, shape and charge distribution, spin and parity. After that we will go for the binding energy part, semi empirical mass formula, then different type of nuclear model including liquid drop model, cell model. Cell model is mentioned later on. So liquid drop model, cell model and collective model. So these are the three model, and other than that Fermi gas model is also there, which will cover. Nature of nuclear forces. So a significant time we have to invest on nuclear physics, nuclear force, nuclear reaction. Okay, its properties, nuclear potential. So different kind of potential model we'll discuss. Wood suction potential, Yucca potential and all those potential. Okay, deuteron problem is one of the most important thing. So dedicated classes will be there. A dedicated class will be there for deuteron. Evidence of cell structure. So this is basically the this will come from the failure of liquid drop model, which will be successful in the cell model, and cell model also has its some limitations, and those limitations will be removed in going to collective model. Rotational spectra, few questions come from this rotational spectra. Then after that elementary ideas of, okay, then alpha, beta and gamma rays. So out of this, alpha decay is very important, beta decay is also very important, gamma decay little less important, and it is small topic also. And the selection rule, this is a very important thing, selection rule we will be talking about. And after that fission and fusion. Fission and fusion, we need to invest a couple of lectures here in fusion and fusion, nuclear reactions, reaction mechanism, compound nuclear and direct nuclear. So you can see the syllabus is not too large. Even within 15-16 lectures we will be able to cover it. Good morning, Ajay. So I hope you got the syllabus. Now let us start with this basic nuclear properties. In the basic nuclear properties, what we will be discussing? We will be discussing various methods to determine the size of the nucleus. Okay. Then we will be talking about shape and charge distribution of the nucleus. So with the help of quadruple moment, we will be talking about the, we will be discussing the shape and what kind of charge distribution is, whether it is spheroid or oblate spheroid, correlate spheroid. We will be talking about that. And those who are preparing for BRC exam, this nuclear physics and particle physics part is very crucial for them. Now without any further ado, let's start with this. So if you want to know about the nucleus, the the basic model which we need to know is the Rutherford's model. So you must have read about this Rutherford model in your maybe class 6 or 7. So what he did, he sent alpha ray to a very thin gold foil, and this one you can see, this is the detector placed around all of it. So when alpha ray is sent through this gold foil, he observed that most of the alpha rays got undeflected. Only very few got reflected back, and few of them is deflected by some angle. So from that experiment, he concluded that most of the portion of the atom is empty and all the mass is concentrated to a very small region. So he later named that portion as the nucleus, where most of the masses of an atom is concentrated. So this is roughly Rutherford's model, Rutherford's experiment, you can say. So based on this, Rutherford gives his atomic model. Now before Rutherford's atomic model, another model was there, plum pudding model. Plum pudding model was given by J.J. Thomson, but plum pudding model failed to explain certain experimental results associated with the atomic structure of the elements. Later on, Ernest Rutherford, who was a British scientist, he conducted an experiment. Based on the observation of the experiment, he explained the atomic structure of the elements and proposed Rutherford's atomic model. Good morning, Mulli. So look, in the initial few slides we have a little bit of theory. So I will upload this PDF, so you can go through it later on also. You don't need to write. So this is the important for your for your foundational understanding. Now what we had in Rutherford's alpha experiment, alpha scattering experiment, actually the same thing has been shown here. So from the radioactive source, alpha ray has been generated and it is passed through some gold foil, and as you can see, wherever the scattered alpha ray strikes, it glows. Rutherford conducted an experiment by bombarding a thin sheet of gold with alpha particle. Then he studied the trajectory of this particle after the interaction of the gold foil. He directed a high energy beam of alpha particles, and the gold foil was taken very thin, at approximately 100 nanometer. So you can imagine 100 nanometer how thin it is, in order to study the deflection caused by the alpha particles. And this screen is the fluorescent screen. Fluorescent screen is that screen, if some radiation falls on a fluorescent screen, it glows. So to identify where the particle is striking, he placed this fluorescent screen. He placed a fluorescent zinc sulfide screen. So sometimes in an interview you are asked, what is fluorescent screen? Give some example. So zinc sulfide is an example of fluorescent screen. Now Rutherford made certain observations that contradicted the Thomson's atomic model, which was based on plum pudding model. Now what was the observations of Rutherford's alpha scattering experiment? So you already know it. Let me just briefly tell you this. The first thing he observed, that a major fraction of the alpha particles bombarded towards the gold sheet passed through the sheet without any deflection. Hence most of the space in an atom is empty. This is the very first observation he made. Secondly, some of the alpha particles were deflected by the gold sheet by very small angles, and hence the positive charge in an atom is not uniformly distributed. Positive charge in an atom is concentrated in a very small volume. Okay, look, what does it say? If the positive charge is distributed at some very small volume, what will happen? Only few portion of it will get reflected or scattered. Now imagine the situation where if it is uniformly distributed around the nucleus, then most of them should have been reflected back, right? Most of them should have been reflected back, but only few of them are getting reflected back. From that, he concluded that the mass is concentrated in a very small volume. Third observation he made, very few alpha particles were deflected back, that only few alpha particles had nearly 180-degree angle of deflection. So the volume occupied by the positively charged particle in an atom is very small as compared to the total volume of an atom. So based on these observations, he gave his atomic model. As per the atomic model, the positive charge and most of the mass of the atom is concentrated in an extremely small volume. He then called it as a nucleus. Secondly, he proposed that the negatively charged electrons surround the nucleus of an atom. Nucleus of an atom. So the electrons are distributed in such a way. Three, 3, 6, 7, 8. And electrons surrounding the nucleus revolves around it with very high speed in circular path. He named the circular path as orbits. Electrons being negatively charged and nucleus being densely condensed mass of positively charged particle are held together by a strong electrostatic force of attraction. So what is the nature of this force? Electrostatic. You see, the attraction between the nucleus and the electron, this is Coulombic or electrostatic in nature. On the other hand, nucleus, which composed of proton and neutrons, the force acting between them with what is that? Strong force. Okay, strong nuclear force. So based on his model, some kind of this kind of picture came. Now let us talk about the mathematical aspects of it. Rutherford's scattering. So this was pretty much theoretical idea. Let's talk about the mathematical aspects of it. So give the heading Rutherford's scattering. So this one is important for solving numericals. Okay, imagine we have a nucleus. Okay, atom means you are bombarding the alpha particle towards some nucleus, you can say. So this is the nucleus, let's say N. Its atomic number is capital Z. Okay, if atomic number is Z, if you multiply the charge of an electron, it becomes the charge of that nucleus. Okay. Now, if you send an alpha particle towards this, what will happen? Let's say an alpha particle is coming, so it will go like this, and after reaching the minimum distance, after reaching a certain distance, it will change its course and it will get deflected. The distance of closest approach, after that it will get deflected. So you can imagine it in this way. Okay, so your alpha particle or any particle, we are not specifying what exactly it is, let's say any projectile. the projectile has atomic number, let's say small z, so its charge will be z times E. So it is going like this and getting scattered by this nucleus. This is your nucleus and this is your projectile, let's say. So as you can see, this is your initial direction, this is your initial direction. Now this projectile, after being scattered, changes its direction. Instead of going along this direction, it is going along this direction. Understood? So we are showing the direction along which we are conducting the experiment. So to measure the angles, let's say previously it was coming along this angle, it's alpha, and this angle is alpha. So this was the initial direction. As you can see, try to understand it very carefully, it's very important. Okay, this was its initial direction and this is its final direction. So what is the angle of scattering? This is the angle of scattering. Can you say it? This will be the angle of scattering phi. This was the initial direction, this is the final direction. So this angle will be the angle of scattering. Now if we join the nucleus with the projectile, so this angle is, let's say, theta, and you know it very well that the perpendicular made on the incident direction, this is known as impact parameter. So let's say this is m. So impact parameter we are denoting by P. Okay. So in Rutherford experiment, what he found in Rutherford's experiment, scattering, a positively charged particle of charge ZD. We are giving a general theory, that is why we are not taking any specific particle like alpha particle or a specific nucleus like uranium. We are not taking, we are keeping it general. A positively charged particle of charge small jd and mass m is scattered by a heavy nucleus, let's say N. So the charge on the nucleus, if the atomic number is capital Z, the charge on the nucleus is capital ZE. So to distinguish between them, for a small z you can give this cut, for capital Z you don't give the cut, where capital Z is the atomic number of the nucleus. So as a reference you can write few things. So these are the standard results we generally use. Z we take alpha z is equals to 4, sorry, z equals to 284 होता है ना, z is equals to 2. The nucleus you can take, maybe gold nucleus you can take, or gold. Let's say gold foil he used, Rutherford used, so Z is equals to 79. So as you are using capital Z, let's write capital Z. Instead of gold, we can also have silver. For silver, the atomic number is 47. In your examination, any of them can be given. P here, P is the impact parameter. In the shown figure. So from this you will get the Rutherford scattering cross section. This formula is very important. Rutherford's scattering cross section. Rutherford scattering cross section is given by sigma, which is a function of the scattering angle phi. This is equals to 1 by 4. You need to remember this expression. Small z, atomic number of the projectile, capital Z, atomic number of the nucleus. Look, one E from this, another E from E, so it becomes E square divided by 4 pi epsilon naught times 2 into E. E is the kinetic energy of this projectile whole square into cosec to the power 4 pi by 2. So just remember, phi is the scattering angle. Alpha doesn't carry so much significance, only the scattering is important. Initial direction and the final direction. The angle between the initial direction and the final direction is the scattering angle. So this formula you need to remember. So as you can see, it is proportional to Z square. It is proportional to 1 by E square, and it is proportional to the fourth power of cosec phi by 2. So let's write it. That is, the scattering cross section. What is the definition of scattering cross section? Number of particles scattered per second along the direction phi is proportional to number 1, the square of the charge on the nucleus. The square of the charge on the nucleus. Capital Z. The square of the charge on the projectile. Okay, proportional to cosec to the power 4 5/2, and fourth one inversely proportional to the square of the initial kinetic energy of the projectile. Let me know once it is done. Nuclear physics is like one of the easiest subject. Here things we will get very easy. I hope this is done. Let's give you a problem. Can you solve this problem? So easy problem. Proton and alpha particles of equal initial momenta are scattered off a gold foil in a Rutherford scattering experiment. The scattering cross sections for proton on gold and alpha particle on gold are sigma p and sigma alpha respectively. The ratio of sigma alpha by sigma p. What is the answer? Simple, na? Tell me quickly. A, B, C, D. Which one of the options is correct? Just apply the formula. Scattering cross section, on which thing it depends? So here variation is there on the projectiles. Now one time the projectile is proton, another time the projectile is alpha particle. So you know na, the scattering cross section sigma, it is proportional to z square. So sigma alpha by sigma p, what will be its? Z alpha by Z proton square over. What is proton? Proton means 1h1. What is Z value here? 1. And alpha, what is alpha? Alpha is 2He4. What is the Z value? 2. So 2 by 1 square 4. That is the answer actually. Yes. So simple problem. Look, when we study things individually, it appears to be very easy, but the real problem is in your examination when you apply the concept. So it is very necessary to identify like which formula will be applied here, which concept will be applied here. That is the main challenge. Otherwise things are pretty simple. And how you can develop that attitude? By solving lot of questions. Then you will understand like where we should apply what. Okay, now let me give you a numerical idea about the size of an atom. So atom is roughly 10 to the power minus 8 centimeter, and in terms of a meter you can say 10 to the power minus 10 meter you can say. Nucleus on the other hand, the size of a nucleus, so this is the whole atom, and if you zoom in the nucleus, it's 10 to the minus 12 centimeter or 10 to the power minus 14 meter. And each nucleon, proton and neutron, we have already discussed that they are made up of quark structure. So you can see 3 quarks, a proton and neutron. So that becomes 10 to the power minus 15 meter, the size of a proton or neutron. And as you go, so 10 to the power minus 16 or 18, 16. So it is less than 10 to the power minus 19 meters. So it is very small, you can say. This is the quark. So the ultimate, you cannot break up further. An electron, very small particle, 10 to the power minus 19 meter, lightest particle. Now, nucleus, it has equal number of, in symmetric stable nuclei you have equal number of proton and neutron. Okay, so number of proton inside the nucleus, number of proton inside the nucleus denotes its atomic number. Okay, so it generally, number of electrons and number of protons are same, but number of electron does not define the atomic number. Number of proton define the atomic number. Okay, remember this thing. Sometimes students get confused here. So 2 things are there. These are very basic thing. Atomic number. Atomic number is denoted by Z. Atomic number is the total number of proton. Then after that we have mass number. Mass number is denoted by A. What is this mass number? Mass number is the total number of nucleons. Total number of nucleons. Nucleons means both proton and neutron. Total number of protons plus total number of neutrons. So that gives you the mass number. Total number of proton is denoted by Z. Total number of neutrons is denoted by N. So A is Z plus N. So whenever we represent a nucleus, how do we represent? Representation of a nucleus. So this is the representation of a nucleus, not an atom. You represent it by specifying its Z value, then X value then A value in this way, like 2 He 4 7 N 14 8 O 16 and so on. 92 uranium 30. I hope this is done. Let's talk about the three definitions: isotopes, isobars, and isotones. Do you know the difference between isotopes, isobars, and isotones? What is isotope? Look, before I discuss isotope, let me just break it again. Z, X, A. So here, number of protons is equals to Z, number of neutrons equals to N, which is equals to A minus Z. Okay. A mass number equals to A. Now isotopes. What do you mean by isotopes? So there exists some nuclei whose atomic number are same but mass number are different. For example, 1H1, 1H2, 1H3. So Z value is same, A value is different. So isotopes are nuclei. Nuclei, nucleus is a singular form. Nuclei is the plural of nucleus. Many nucleus is nuclei. The nuclei with same atomic number Z but different mass number A. For an example, the very famous protium, deuterium, tritium. These are called isotopes. Isotopes. Isobars. Bar means it is talking about weight. Isobars means nuclei with same mass number. Just the opposite of it. Nuclei with same mass number but different atomic number. For an example, the case of oxygen 8O16, and if you take 7 and 16, so both have same mass number, so these are isobars. Another thing is isotones. Look, isotones, at the end you are getting tones, neutrons. So isotones mean, iso means equal. Remember this one, iso Iso means equal. Isotope, so equal atomic number. Isobars equal mass number. Isotones equal number of neutrons. Nuclei with the same number of neutrons. So if you take the example of, let's say, oxygen 8O16. So here how many number of proton is there? Proton is 8, neutron is 8, 7 and 15. Here proton number is 7, neutron number is 8. 6C14. Here proton number is 6, neutron number is 8. So for all of these, neutron numbers are same, so these are called isotones. What happened to my throat? Just let me know when you are done. Okay, let us talk about mirror nuclei. Mirror nuclei and nuclear radii determination. So mirror nuclei method is one of the method to determine the size of a nucleus. So as you can see in this example, look at this. It is like a mirror has been placed here. It has, let's say, 2 proton, 1 neutron. So red one is proton and this little green one is neutron. So here 2 number of protons were there, 1 neutron was there, but here you see 2 neutron and 1 proton. So it is like a mirror image has been taken. So 2He3, here number of neutron is 1, here number of neutron is 2. So 2 1 is there, it is like 1 2, but the at mass number is same. Same thing goes here. It is like you have placed a mirror. 4 number of proton are there, 3 number of neutrons are there. Here you see 3 number of proton is there, 4 number of neutrons. It is, you see, the mass number is same, but the number of protons and neutrons are interchanged. So that is the definition of mirror nuclei. Mass number are same means they are isobaric nuclei. So a pair of isobaric nuclei are known as mirror nuclei where in the nucleus the proton number Z and the neutron number N are interchanged and differ by, in both of these example you can see number of proton is differ by 1 unit only, 1 2 3 4, and differ by 1 unit. Few more example we can take. So a general example we can set it like this. Let's say you have placed a mirror. So this is a rough surface, let's say. If you have a nuclei, let's say X, so its atomic number is Z, mass number is mass number is A, neutron number is N. So if you take a mirror image of it, so mass number is not changing, A, Z becomes N, N becomes Z. You see, the atomic number has been changed. It was Z, now it has become N. So the nuclei is changed. So you cannot write X, we have to write Y. For an example, 6C13. So what is this neutron number? Is 7. So it is like the mirror image of here 7 6 6 7 will become 7 6, right? 7 6, and this mass number will be unchanged. So 7 is nitrogen. So these are the examples of mirror nuclei. So as you can see, they are differing by 1 unit. So we can calculate the difference in their Coulomb energy. The difference in Coulomb energy let's say it is denoted by delta EC between two neighboring mirror nuclei of charges. You see, if Z and N differ by 1 unit, so Z minus N, if this is 1 unit, what you can say? If you take the atomic number of one mirror nuclei, one mirror nucleus is Z, another one will be Z plus 1, then only they will be differ by 1 unit. The difference in Coulomb energy delta EC between two neighboring mirror nuclei of charges Jd and Z plus 1, this is the atomic number. If you multiply with energy, electronic charge, it becomes the charge. Now you see, their atomic number is differing by 1 unit only, so their radius will be similar, of the same order, having the same radius. Using this concept that the neighboring mirror nuclei have the same radius, we can determine the radius, that is the size of the nucleus. So the formula goes like this: delta EC, difference in their Coulomb energy, is equals to 3 by 5 E square by Rn into Z plus 1 whole square minus Z square. So this is your mirror nuclei formula. So lot of questions come from this. Let me give you a question based on this mirror nuclei. Is it done? Try to solve this problem. Came in December 2011. The difference in the Coulomb energy between the nuclei, mirror nuclei 24 Ce 25 24 Cr49 and 25 Mn49, it's 6 MeV. So delta Ec is given to you. The greater one, okay, so smaller one is Z, the greater one is Z plus 1, atomic number I'm talking about. Assuming that the nuclei have a spherically symmetric charge distribution and E square value is 1 MeV Fermi, what is the radius of this nuclei? Do it quickly. Could you solve this problem quickly? Do it quickly. Delta Ec is equals to C by 5 E square by Rn Z plus 1 whole square minus Z square. This is the formula, right? Delta Ec is 6 MeV. 3 by 5 E square is 1 MeV femtometer. So let's keep it Rn. It is 25 square minus 24 square. So Rn it will come in which unit? We have put MeV femtometer, so Rn should come in femtometer, right? Three by 30, 25 plus 24 into 25 minus 24. So 1 into, okay. So how much it is? 4.9 femtometer. 1 femtometer is 10 to the power minus 15 meter. Option B. Is it clear or not? Is it done? Should we move forward? Hari Ajay Murli. In the next slide, we'll be talking about binding energy of a nucleus. Try to understand this binding energy very well. Binding energy of nucleus. We'll try to understand this with pictures. What is actually the binding energy? You know, whenever we consider, let's say, a nucleus. So inside the nucleus, we have the protons, neutrons, all of them bounded together. Proton, neutron. So they are bound by some force. So if you want to separate them up, if you want to separate them and you want to produce individual proton and neutron, we need to impart some few MeVs of energies. So this energy is known as binding energy. The amount of energy you require to separate these proton and neutrons is known as the binding energy. It is represented by EB. Now what is the source of this binding energy? So what actually happens if you consider an atom, let's say. First of all, let's consider the atom. So inside the atoms we have the nucleus and the electrons are outside. Now imagine a thing, it is positive. Here we have our proton, neutron, and outside it we have electrons. How many electrons will be there? How many electrons will be there? Number of electrons will be equal to number of protons. For a neutral atom, if you consider, let's say, a neutral atom, so for a neutral atom, number of proton is equals to number of electrons. Z is equals to क्या लिखें, number of protons equals to number of electrons. Now what is the source of this binding energy? You know, if you want to separate, so what we have electrons, we have proton, neutrons. I'm just showing you few of them. Now if you calculate the energy of these particles individually, whatever energy you will get, and the energy of the atom, so this, let's say E prime, this energy E prime will be less than E. So we have little less amount of energy inside this bounded atom. So that amount of energy, actually the mass, energy will come into picture later on. if I talk about the mass, the masses m prime will be little less than m. So this missing mass is the source of the binding energy. Is it understood? E is equals to mc square formula. So m prime and m minus m prime, that is the missing mass. That missing mass is the origin of the binding energy, and that is what we will be calculating. That is what we will be using for calculation of the binding energy. Is it clear? So let's say from the constituent elements to this whole neutral atom, delta m amount of mass being disappeared. So if delta m be the mass amount of mass disappeared, then the energy EB, this is the binding energy EB, will be delta m time c square as per Einstein's mass energy equivalence. Now mass of a proton is mp, mass of a neutron is, let's say, mn, and mass of the electrons, let's say, me. Then what you can write? Delta m is equals to how many number of protons we have considered? Z number of protons. How many number of neutrons? N number of neutrons. So n times mass of neutron. How many number of electrons? Same number of protons. Okay, plus Z times mass of an electron. Now what is the mass of an atom? Mass of an atom is represented by mass with atomic number mass number A, atomic number Z. So this is the mass of the atom, atomic mass m. Is it? Can you write it? M of Az is the mass of the atom of mass number A and atomic number Z. We are doing the calculation here as we don't have space, sufficient space. So what will be our EB? Therefore, EB is equals to Z times MP plus N times Mn plus Z times Me minus mass of the atom times C square. So we can write it as Z times MP plus N times Mn plus Z times Me minus. Look, mass of an atom, if you consider mass of an atom, so you can consider it like the mass of nucleus plus that of electrons. electrons and nucleus makes the atom, right? So mass of the atom can be written as mass of the nucleus and mass of the electron. Mass of the electron is Zme. The fun fact is this Zme and Zme getting cancelled. So ultimately we are getting Zmp plus Nmn minus mass of the nucleus, let's say MnUc times c square. So this is the formula of the binding energy. This formula you will be utilizing every time. Zmp plus Nmn minus mass of the nucleus times Is it clear or not? Let me give you one problem. Try to solve this problem. Total binding energy of the 2He5 nucleus is approximately equal to mass of the nucleus you are given in terms of U. What is U? 1 U is equals to 931.5 MeV per c square. So this is the unit of mass, that is the MeV per c square is coming. Do it quickly. Harry, Ajay, Murli, guys, are you able to understand these things? Let me know. I assume that you are understanding everything. In fact, there is nothing complicated here, simple things. You just need to do it in a systematic way. Not able to do this simple problem? 2He5. 2He5. So its atomic number is 2, number of proton is 2, mass number is 5. So what is neutron number? A minus Z. 5 minus 2 is 3. So 3 protons, 3 neutrons are there, 2 protons are there. So what is the binding energy? Z times MP, N times Mn minus mass of the nucleus times C square. Okay. So Z is 2 here, 2 times mass of proton means this, 2 times mass of 1H plus N times means 3 times mass of neutron. So in the question it is given Mn minus mass of nuclei means mass of 2He5 times C square. Now you see the masses are given in terms of U. So 2 into 1.007825 U, okay, U let's take common, plus 3 times 1.008665 minus 5.01220, you see, into 931.5 MeV per C square, and C square is getting cancelled, so it is only MeV. So if you calculate it, we will get 0.02944 and 931.5 MeV, that will give you around 27.4 MeV. Option D will match. Clear? Although in your examination you will be allowed to use calculator, so you don't need to worry about these lengthy calculations. You can easily do it in seconds. Okay guys, I could not see your comments. Now I just refreshed and seeing your comments. Okay, sorry guys. Okay. Karthik, shouldn't we go for converting energy to joules? Can you keep it as mega electron volt itself? Now you can comment guys, if any more questions you have. Actually I could not see your comments. Actually it was not getting refreshed, so the comment were stuck. Now is there any question? Karthik, Ajay, Harry, Mulli? If there is no question, we can go for mass defects. One thing, as Karthik asked, in nuclear physics, we generally take up this unit MeV. The order is of the order of MeV. So here we don't convert MeV into joule. Generally, whatever unit are given, we generally try to keep it in MeV, because that is the order of the nuclear forces. Mass defect. Let us talk about mass defect. What is mass defect? In simple terms, if we can say, mass defect is the difference between the mass of an atom and the mass number. Now let's take the case of oxygen 16. So here the mass number is 16, but if you see the atomic mass of oxygen is not exactly 16 but 15.994915 atomic mass unit. Okay, so there is a slight difference, and this difference is the mass defects. This mass defect, it may be positive, it may be negative. Both of them can be happen. In case of deuteron, you can say deuteron consists of one proton and one neutron, right? The deuterium nucleus consists of one proton and one neutron. So proton has a mass, you can see 938 MeV, neutron has a mass 940 MeV, but the deuterium as a whole has a mass of 1876 MeV. So you can see it is, if you add 938 and 940, it is 1878. So around 1.8 MeV is extra, na? That 1.8 MeV is like heat or energy. So this difference is the mass defect. So you can write a definition. The difference between the, in negative example, we'll talk about it. The difference between the measured mass, the measured atomic mass represented in this way, m of Az expressed in U. U is the atomic mass unit, okay, AMU, in short U, and the mass number A of a nuclide is called the mass defect. Delta M. So you can mathematically express it delta M. Okay, delta you represented by delta M prime. Previously we have used delta M for other things, so let's use delta M prime for this mass defect. This is equals to atomic mass minus the mass number. Okay, let's take some example. What is the mass defect of, let's say, He4 helium? It will be, look, its mass is 4.002603 minus mass number is 4 mu. So this is plus 0.002603 mu, and that of oxygen 16O is equals to, you see, its mass is 15.994915 and minus mass number is 16, so it is coming in negative how much, 0.005085 mu. Note that the mass defect can be both positive and negative. As you have already seen, experimentally it has been found that the mass defect delta m prime is positive for very light and very heavy atoms, and it is negative for atoms in between the two. So very light and very heavy mass defects are positive, and in between mass defects are negative. You can see this helium, it comes in the very light category, it's positive, and oxygen, it's coming between very light and very heavy, so mass defect is negative. Now closely related to this mass defect, there is a term called packing fraction. There is a term called packing fraction. Let's talk about this packing fraction, then we'll wrap up the thing. Simple thing, packing fraction, small thing, it will not take much time. What is packing fraction? Packing fraction is mass defects per unit mass, or mass defect per nucleon. A is what? N plus Z. So A is what? The total number of nucleons, right? So if you divide the mass defects by the total number of nucleons, that gives you packing fraction. So it is defined as the mass defect per nucleon in the nucleus. So if you represent packing fraction, it is represented by F, packing fraction F. So F will be equals to delta M prime divided by total number of nucleon is A. So M prime, we have got mass of the atom minus the mass number and divided by the mass number A. So this is M of Az divided by A minus 1. So we can express mass of the atom in terms of the packing fraction by this expression of So you see 1 going on that side, 1 plus F and multiply by this A. So this is the expression used to represent the mass of the atom in terms of the packing fraction. Okay. So I think this is enough for today. We'll continue from here. On the next day, we'll start with binding fraction, and from that we'll be discussing, we'll be explaining the binding energy curve. A lot of things are there. We will be taking up those things in the next session. So this is all for this session, guys. Thank you very much for joining this session. If you have any question, query, you can let me know, and those who are new to this channel, please subscribe the channel and don't forget to press the bell icon. Try to attend live. I am not sure whether this class will remain live or not, so try to attend live, those who are not enrolled. And for enrolled students, this lecture will be available in your course folder. Okay, thank you very much. Bye bye, take care.